Section 6.1, Solving Systems by Graphing. A system of linear equations is a set of two or more linear equations containing two or more variables. So once again, a system of linear equations is a set of two or more linear equations containing two or more variables. A solution of a system of linear equations with two variables is an ordered pair that satisfies each equation in the system. So once again, a solution to a system of equations with two variables is an ordered pair that satisfies each equation in the system. So we want to look at solving this first example by graphing. So we're going to graph each of these lines and see where they intersect. Because at the intersection point is the value for which x and y that satisfy both equations. So we'll graph the first one. This first equation has an y-intercept at 0 and is a slope of 1. So we're going up 1, right 1, up 1, right 1. And so we graph the values accordingly. And then we connect our dots, extending our slope the other way as best we can. And that's our line. Then we're going to graph the second equation. This has a y-intercept of -3 and a slope of -2. So we go down 2, right 1, down 2, right 1. If we want our points on the opposite direction, we go up 2, left 1. We get enough points to graph, and we connect our points to make our line. So there's a second line. So for this problem, our intersection point is right here. So the solution to this system is the point -1, -1. So if we plugged in -1 for x and -1 for y, it would be true in both equations. Example 2, we're going to do the same thing. We can graph the first one because it's in slope-intercept form. So we plot our intercept at -3 and apply our slope, up 1, right 3, up 1, right 3. We want our points in the opposite direction, we go down 1, left 3. We connect the points to make our line. The second equation, however, needs to be rewritten into slope-intercept form. So in order to do that, we have to move the x to the other side of the equation. So we subtract 2x from both sides. So you've got y equals -2x plus 4. Now we can graph this. So we start by plotting our y-intercept at 4. We're going to go down 2, right 1, down 2, right 1, down 2, right 1, and so on. And then we connect our points to make our line. And there's our second line. These two lines intersect right here at the point 3, -2. And so this is our solution. Example 3, same thing. Both equations are in slope-intercept form, so we can graph them right away. Our y-intercept for the first one is -1. We apply our slope, down 2, right 1, down 2, right 1, down 2, right 1. We want to connect our points in order to make our graph. And there's our graph. We're going to do the same thing for the second equation. We're going to plot our intercept at +5. Apply your slope, up 1, right 1, up 1, right 1. We can go down 1, left 1 to get our points in the other direction. And so our graph looks something like this. Remember, the solution to your systems is the intersection point, so we're looking for the point where they cross. And in this case, our solution should be -2, 3. And so that's the solution to this system. Now we're dealing with a word problem. Katie and Kelly are reading the same book. Katie is on page 14 and reads 2 pages every night. Kelly is on page 6 and reads 3 pages every night. When will they have read the same number of pages? And what will that number be? So we first have to figure out our two equations. So let's let y be total pages and x be, in this case, nights. So our equations for this one, so we can start by we'll write Katie's equation first. So Katie's equation, she's going to have the total number of pages is going to be equal to the 14 pages she started with plus 2 pages every night. So you can write it like that, or you could write it like this so it looks like it's more in slope-intercept form. Kelly's equation, on the other hand, slightly different but same format. You've got the total pages is equal to the number of pages she currently has, 6, plus the 3 pages she reads per night. But once again, you can flip that around so it looks like it's more in slope-intercept form. So y equals 3x plus 6. And what we'd want to do is we want to graph these two equations and see where they intersect. So if you graph these two lines on your grid provided, you get that the intersection occurs at 8:30, which means that after 8 nights, both girls will have read 30 pages, which takes care of our two questions. And the next one, Family Video charges $10 for membership and $3 per movie rental. Blockbuster charges $15 for membership and $2 per movie rental. For how many movie rentals will the cost be the same at both video clubs? What is that cost? So we're going to do the same thing here. We got to set up our equations. So I'm going to let y equals cost, total cost, and x equals movies or rentals. So for Family Video, we've got total cost is going to be equal to the $10 membership plus the $3 per movie. Or once again, we can write it so it's more in a slope-intercept format. So y equals 3x plus 10. And then Blockbuster, same thing. We've got total cost equals the membership charge of $15 plus $2 per rental. And so what we want to do is we want to graph both of these and see where they intersect to figure out our answer. And so if you graph both of these on the grid provided, you learn that your intersection point is at 5:25, which means that for 5 movie rentals, the cost will be the same at both places, which is $25. All right, so there are different types of systems of linear equations. Sometimes you get one solution when they intersect at one point. Sometimes you'll have infinitely many solutions, is when you have the same line. And then sometimes you have no solutions when your lines are parallel. All right, so one solution, they intersect at one point. Infinitely many, it's the same line in both cases. And no solution means they're parallel. All right, so we want to go ahead and graph these and see what our solution would be. Well, in both cases, we have to rewrite both equations. So in this first one, I've got to get y by itself. So that means I probably need to divide by 3 throughout. And when I do this, I get y equals 1/3 x plus 1. All right, that one's ready to be graphed. In the second one, in order to get y by itself, I need to add 1/3 x to both sides. And so that gives me y equals 1/3 x plus 1. And so now I just want to graph these. So I'll start with the first one. My intercept is at 1. My slope is 1/3, so I'll go up 1 over 3, up 1 over 3. I'll go backwards to get my other points, and this is my line. Then I'd graph the second one, and immediately I start noticing some similarities. My intercept's at 1, and my slope is up 1 over 3, so I'm hitting the same points I've already done. So in this case, and I kind of noticed it before I started graphing them, these two equations are the exact same. So that means we have infinitely many solutions because they are intersecting at every single point along the line. And then the last one, we want to do the same thing here. We want to rewrite our equations because neither of these is in slope-intercept form. So for the first one, I've got to subtract x from both sides. So I get y equals negative x plus 5. In the second equation, I need to subtract 4 from both sides. So I've got y equals negative x minus 4. And now I just want to graph these. So I start by plotting my y-intercept for the first one, and I go down 1, right 1. So my line looks something like that. For the second one, I start with my y-intercept at negative 4, and I apply my slope. Down 1, right 1. And you plot your line. And in this case, our graphs do not cross. And so before we even graph these, we should have noticed that they have the same slope. So that means they're parallel. And so parallel lines have no solutions.